For today's video, I just want to teach a concept again. So since we're only doing a concept, we're not actually going to be doing any real math. I just want to establish some background information so that way in the next video when we do some real math, you'll already understand what we're looking for and what's going on. So today, as you can see, we're going to look at concavity. Now, concavity is another thing that's going to help us understand the shape of a graph without actually having to use a calculator and look at the graph, right? How is it going to help us? Well, we have two things. We have concave up and concave down, right? So a graph can be concave up and it'll look like this. Or we can have a graph that's concave down and it might look like this. And it kind of looks like the minimums and maximums we've been working with, right? And you might be able to look at this and come up with your own little definition of concave up and concave down. You might say, okay, well, concave up, we have a minimum, right? Probably a relative minimum. So we're going to have some critical point somewhere. And on the interval to the left of the critical point, our slope is always going to decrease. And to the right, it's always going to increase. And then you might say the opposite for concave down. You're going to say, oh, well, we have a critical point. And on the interval to the left of the critical point, our slope is increasing. And to the right, the slope is decreasing, right? And I might give you some credit for that definition. I mean, it makes sense, right? However, it's not always going to work, right? Why won't it always work? Well, what if I told you that this right here is concave up? And then this right here is also concave down. Just that little interval contained within the pink boxes, right? Your definition wouldn't work anymore, right? There isn't even a critical point in either of those boxes. And in fact, in both of those boxes, in those intervals, our slope is decreasing the entire time. Yet one is concave up and one is concave down. So how can we establish some definition of where an interval is concave up? Well, it turns out that an interval will be concave up when the line tangent to every single point on that interval is below the graph, right? So if we draw a ton of tangent lines, all to every single point here in this interval, it's all below the graph, and that extends for the entire time that we're concave up. And then the opposite is true for our concave down intervals, right? An interval is concave down if at every point the tangent line is above the graph, right? So our little tangent lines are all above the graph, and that's going to go for the entire interval that's concave up. So what if we have a situation like this, right? We're looking at a continuous graph, and it looks like this. So clearly, there's a relative max and a relative min. One of them is concave down, and the other is concave up. But where is the switch, right? You might say the switch is somewhere right in between, like right in the middle, but we can't say for sure because, well, what happens at that switch? Well, we know for concave down, tangent line is always going to be above the graph, right? And then for concave up, tangent line is always going to be below the graph. So there's got to be some point where it switches over, right? We call this point the inflection point, right? If our graph is continuous and it switches from being concave down to concave up, or the opposite, concave up to concave down, there is some point in between called the inflection point where our concavity changes. And in the next video, when we start doing some math, we're going to find how we can get these inflection points. If you made it to the end of this video, thank you for watching. I really appreciate it, and I hope you learned something.